Hi, I'm Grazia Zambella, PhD student of the Information Engineering Department of the University of Pisa. I collaborate also with the Research Center in Viaggio and with the Italian Institute of Technology. In this video, we show you our research line about the control of the humanoids robot. Humanoids diffusion increase in the recent year. This happens because they can favor social interaction, they can perform the communication task, and they can locomote around. Among all the humanoids in the world, the two-wheeled ones have the most efficient and the fastest mobile base. For this reason, they can be employed in warehouses or in the hospital to help workers with their daily task. But before to make this reality, we need to avoid a situation like the one shown in the video, where the robot falls down while it is interacting with the environment. We decided to tackle this problem from a control point of view, and therefore we decided to move from the traditional control approaches that divides the control of the mobile base from the control of the upper body to a new dynamic or body control approach. The dynamic control approach that we present in this video makes the robot upper body actively cooperate with the mobile base to balance this robot. At first, we go to define the robot model from a kinematics and dynamics point of view. As regards the kinematics, we can describe this robot as a floating base mobile robot that moves on a flat, non-slippery surface. As regards the dynamics, we can use the dynamic equation applied to the constraint system because we can consider the pure grounding constraints between the wheels and the ground. These constraints are non-holonomics, and for this reason they can be written in the Pfaffian form. In this equation, we go to find tau, that is the vector of the torque of actuated joints. The first step to design our control approach is to solve the constraint dynamics. Therefore, we applied the methods of the quasi-velocity. We go to define the vector n as the vector of quasi-velocity that is composed of the forward linear speed, the yaw rate, and the pitch rate, and the velocity of the joints of the arm. At this point, we can write the dynamics equation in terms of quasi-velocity, and we can apply a computer torque control approach to find the torque tau tilde that makes null the second aerodynamics of the quasi-velocity. But we need to find tau and not tau tilde. So we need to invert this equation, but the matrix U tilde is not square. If we expand this formula, we can see that the first and the third row of the matrix U tilde that are relative to the forward linear speed and to the pitch angle are linearly dependent. So we can neglect the first row and we can invert the obtained subsystem to find the torque tau. To validate this control approach, we applied it on Alter Ego, that is a two-wheeled robot built by the Research Center Enrico Piaggio and the Italian Institute of Technology. We implement the control approach on ROS, and we perform different experiments. At first, we apply a static disturbance on the robot, putting some weights in its shopping bag. Then we push the robot in different parts of its body to simulate a dynamics disturbance. And to conclude, we analyze the behavior of the robot while it is interacting with the environment. In all this experiment, you can see that the robot arms help the wheels to balance the robot and to acquire the desired position. To conclude, I show a whole body control approach that stabilizes two-wheeled humanoids, making the robot upper body actively cooperate with the mobile base, and that guarantees also the respect of the kinematic constraints without solving optimization problem. I show you also the efficacy of these methods with the experimental validation on Alter Ego. Thanks for your attention.